Dear Professor, welcome. I would just like to start with a preface in regards to physics itself and my own interest with physics. To be honest with you, the interest in physics on my behalf has been steadily waning ever since I started going to high school. So that was like what, around 9 to 10 years ago. But I can remember back like when I was 9 years old, I remember reading encyclopedias and reading about Einstein's general theory of relativity. And all of that was really, really exciting for me and really interesting, to find out the ways that the world works and to find out the ways that the world itself interacts with, several parts of it. And your book, Fundamentals, 10 Keys to Reality, had kind of brought me back to that childhood interest, had evoking emotions within me, but also the general interest. And I just really want to thank you for writing that book and for being a part of this podcast.
Thank you. Yeah, writing that book was a similar experience for me. I mean, of course, I've been researching at frontiers of physics and science now for quite a few years, but and when you do that, some of the original kind of curiosity and questioning and big questions that motivated the movement for me into that field got kind of not lost, but kind of diluted and forgotten. And going back and thinking about those big questions, thinking about the kinds of questions my friends asked me about what I was doing, my intelligent but not necessarily up-to-date friends, it was a great experience. It was a great experience, and I think it got me back in touch with reality in a way that I didn't anticipate.
And I think I have a feeling, and you can correct me if I'm wrong, but I have a feeling that this is something that you basically alluded to in the beginning, in the introduction of your book. Among other things, I'm a really big fan of poetry and of philosophy, and the 4 verses from William Blake that you mentioned in the introduction really were really inspiring, and I can testify to this. My friends can confirm. I've sent it like 3 to 4 other people because I didn't know of the verses prior, and I'm just gonna read them so we can perhaps build our conversations from there.
All right.
So William Blake: to see a world in a grain of sand and a heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. Where does, you mentioned previously that your return to the big questions, where does this infinity in the palm of your hand lie right now? Where do you find the most magnificent of ideas, or the most magnificent idea of physics in the present moment?
Well, let me answer that in 2 ways. One is, in general, the idea or the fact that the best way to understand the physical world is to sort of start small and understand the basic building blocks and their interactions thoroughly, and then to build up is maybe the most profound result of deep inquiry into the physical world, that you can formulate laws that are precise and mathematical, that act locally between the different basic building blocks of matter, and that really is the world's operating system, and allows you to build out from there is the general answer. And it means that William Blake's vision that you can hold infinity in the palm of your hand has an almost literal truth to it when you understand things deeply, even very small things, connect to the structure of the whole universe. I mentioned that at the level of understanding them thoroughly will enable you to understand the universe, and it also works the other way. Understanding how the history of the universe could have resulted in things like flowers is also an extraordinary revelation and a mind-expanding revelation. So that's the general framework. But let me tell you a specific example now that's now at the frontier of science and physics and my own research, which is the problem of dark matter and the problem of understanding the basic laws more profoundly, which turn out to, again, make a remarkable connection between the very small and the very large. Problems in fundamental physics having to do with the fact that the laws look very, very similar the basic laws look very, very similar if you run them backwards in time. You get almost the same laws between fundamental entities if you reverse the arrow of time. So if you took a movie and then ran it backwards, you couldn't really tell that the laws were different. Understanding that has that strange fact about the fundamental laws led us by a long train of beautiful arguments to suggest the existence of a new kind of particle called an axion that would finally explain that. It's been a riddle at the heart of physics for centuries now, but we're close. I think if these ideas are correct, we're close to finally nailing it. So that was a wonderful result of understanding nature better and understanding many of the laws of physics much more deeply. And it was another case of great answers leading to even more profound questions. Why we can, as we know more, we can ask more sophisticated and more powerful questions and address them successfully. So we were led to think that there might be this new kind of particle called an axion. And then meanwhile, astronomers looking out in space have found that they need some new kind of matter, that the kinds of matter that we're made out of, that participate in engineering and chemistry and so forth, aren't enough to build, and that astronomers have been happy to study for centuries now, are not enough to explain what we see out there. In a variety of different circumstances, astronomers have discovered that there's some new kind of matter, which cannot be any of the known kinds, that is seen so far only through its gravitational force. And then the question arises, what is it? And it turns out that these axions have just the right properties to provide that dark matter, so-called dark matter, that the astronomers need and have discovered. It's produced in the right amount during the Big Bang. It interacts very, very weakly with ordinary matter, so so that's consistent with what's observed. However, its interactions with matter are not zero, so we can, with sophisticated antennas and instruments, we can hope to detect it. And that's a big enterprise at the frontiers of physics and cosmology now around the world. And one of the things that I'm spending a lot of my time on now is precisely this, to try to design the kinds of antennas that will show us that this dark matter, this mysterious thing, actually is something that really, really is beautiful and would emerge for quite different reasons in our conceptual universe in fundamental physics.
Yeah, I mean, that's one
so
of the...
It's amazing connection between the basic understanding of how things work at small scales and in microscopic detail of their interactions, and on the other hand, what makes up the universe as a whole.
Yeah, the big unknown, as they would say it, and that was one of the questions that really mind-boggled me once I was like reading through your book. And the question of the dark matter and the dark energy, I believe that you call them like the dark side,
Yes.
in one, or actually two words. And what struck me was the very basic definition behind it. It was like gravitational forces with no visible cause. And another
That's right.
thing that struck me that I remember from watching, I believe, National Geographic, is that the dark matter makes up the 70% of the universe, as they would put it. What is
70% of the mass of the universe. That's right.
above the mass
Yes.
of the universe?
Well, more than that, actually. It's more like 95%.
95%.
Well, between dark matter, so-called dark matter, and dark energy, which are two distinct phenomena. Dark energy is a very bad name. What it means is that space itself has a non-zero density, a very tiny density, but since it's everywhere, it adds up. And that when you add it all up and see how much you need to account for observations, you need about 70% of the mass of the universe to be that. And then there's something called dark matter, which looks like a kind of particle that clumps, but not quite as much as ordinary particles, and interacts with ordinary particles very, very weakly, as I mentioned. And we don't know what that is either, but it's I'd like to think it's axions. It's probably some kind of new elementary particle.
And what's the how would I say, not relevance, but what's the relevance and the immensity of it in terms of the dark matter and dark energy when it comes to the creation of the universe itself?
Well, it's very important for the formation of structure in the universe, for one thing. In fact, the dark matter, which I should hasten to add is not really dark, it's not black, it's completely transparent, it interacts very, very weakly with light. That's the problem. We haven't been able to see it in any, not only because it doesn't emit light, but also it doesn't absorb light, it doesn't do much of anything except gravitate. But what happens in the formation of structure in the universe as we've calculated it, and there's a lot of evidence for this picture, is that very small inhomogeneities in density in the early moments of the Big Bang grow by gravitational instability. Because if you have more mass here than there, then as time goes on, the more massive region will attract even more mass, and there's kind of instability.
Matthew's
and
principle.
That ultimately, what's that?
Matthew's principle.
Oh, Matthew's principle. That's right. The rich get richer and the poor get poorer. Or and if you work out how much matter you need to make that happen, you find that you need much more matter than we can account for in terms of ordinary matter, visible, the kind of stuff we're made out of, and we've spent centuries interacting with and engineering with and understanding very profoundly now. So the dark matter is necessary in order to make that gravitational instability strong enough. And another related observation is that really you should think of galaxies. So it's usually said that every galaxy that's been observed is surrounded by a kind of a halo or cloud of dark matter that's around, and that's a big piece of evidence for dark matter. The gravitational patterns that you see acting on the visible matter is not completely accounted for by the other visible matter. You need some extra stuff. But So each galaxy is surrounded by this by its own dark matter halo. But it would be more accurate to say that the galaxy is an impurity inside the dark matter halo. The dark matter halo is the thing that really formed, and then the ordinary matter fell into it. And that, so really to account for the structure of the universe as we see it, dark matter plays an absolutely essential role. Yeah.
And you mentioned previously, in terms of the dark matter itself, the particles of the dark matter being extraordinarily, and this is just in my limited English, so if I make a mistake, pardon me, but they are extraordinarily close in their properties to axions, actually. And you mentioned some of those properties. You mentioned, I believe, that the axion, interacts with other particles in a really, really limited scope. Which other properties do axions presumably have that dark matter has? And secondly, I know this is like a vague question. How far are we from the actual discovery of axions themselves?
Yeah. Okay. So the properties of axions are fairly precisely predicted by the theory, which they were invented to solve a problem, which I alluded to, of understanding this strange feature of the laws, that they look the same run backwards in time, to a very good approximation. So we can say what their properties are, if they exist at all, and they do have to interact very, very weakly with ordinary matter. That's kind of a specific but weak clue that they have the right properties. A much stronger clue is that if you ask how much would they get produced during the Big Bang, I should say during the very early moments of the Big Bang, when it was much hotter and denser, axions, even though they interact very, very weakly, there was enough stuff around and things were hot enough, energetic enough, that the axions were interacting significantly. And then they kind of decoupled, but they were formed in very large numbers before that happened, before they decoupled. And you can calculate how much is left over. Mm-hmm. And it's just about the right amount to make the dark matter as observed. Mm. So that's the main coincidence, if you like. So it's two things, one of which is very forgiving, namely that the interaction has to be weak enough to be consistent with the fact that nobody's observed the interaction other than gravity. And the second is that it's produced in the right amount to make the dark matter. And there are also some more details about the way that when it's produced, it's cold. When the particles start to move freely, when they're no longer interacting very strongly with the other stuff, that they're not moving very fast. This is called cold dark matter. And axions also have that property, which is important for the details of structure formation. So it has just the right properties, but on the other hand, since we don't know that much about the dark matter, it doesn't take all that much to fit this to be a suspect from that point of view. However, then the second question is, okay, so now how do we go further? How do we prove that it is axions or not? And there, you can consult the theory and see that although the interactions with ordinary matter are predicted to be very weak, they're not zero. And so we have the equations which tell us, in principle, what kind of observations we need to make in order to either find this particle or rule out the whole circle of ideas. And you can think of it as a kind of exotic problem in antenna design. And in fact, You can predict how axions interact with electromagnetic fields, so you can literally try to use axions to excite electromagnetic vibrations, and that's what we're trying to do. And because the interactions are very weak, the signals are very weak, it's only in recent years that the technology of working at low temperatures with quantum devices and especially sculpted materials has gotten to the point where we have a chance of detecting these particles if they're out there. There are still challenges, but I think, well, I would be very surprised if the discovery came next year, but I wouldn't be surprised if it came in a decade, and I would be negatively surprised if we didn't have decisive evidence, say, in 2 decades. So, I'm at the point where I'm trying to take good care of my health and make sure that I hang around long enough to see the day when axions are discovered.
Yeah, but I mean, it's really close in the future. I mean, 10, 20 years is nothing on the grand scheme of things. And I just like to yeah, I mean, this is actually something that I'd like to...
Well, not only that, but in modern physics, where we're looking, well, we understand a lot. So when we try to look for fundamentally new things that we don't understand yet, you really have to push the envelope, and sometimes it's very, very difficult. Now, for instance, 2 recent triumphs of physics are illustrative. The Higgs particle basically was predicted theoretically in the 1960s and kind of firmly predicted in the early 1970s. And people knew exactly what they had to do. They had to build a high energy accelerator and detect certain kinds of tracks and so forth. But it was not until 2012 that it was finally done. So it took a long, long time and a big effort by many people to get it done. And then there was the case of gravitational waves, which are a result of Einstein's general theory of relativity, a very tiny effect that space-time itself shakes up in response to violent motion of big objects. And those were predicted pretty firmly in the early part of the 20th century. And it's only about 100 years later that the technology caught up and people were actually succeeded, that people were able to actually succeed in detecting these things. And that's opened a whole new branch of astronomy. So nowadays, well, sometimes you have to be patient.
But I think it kind of alludes to, I'm not sure if the allude is the right word for it, but it kind of, let's use this synonym, it kind of points towards, from my perspective, from my own point of view, to, I believe, the Einstein's, I believe it was the Einstein's quote, it was certainly within your book, the most incomprehensible thing about the universe is that it's comprehensible. And,
yes.
For me, when I was a kid, and reading, of course, understanding maybe 1% of the stuff that I read about the universe itself, the most kind of interesting thing back then has been the question of the Big Bang and how the universe came to be. And the sub-question within that question, which now I want to ask you, building upon the stuff that you've written about in your book, is, does it even from a philosophical and from a scientific point of view make sense to ask the question, what happened before the Big Bang itself?
Well, we really don't know because our equations don't give the answer. The equations that we have today don't allow us to really address that question. When you run them backwards in time, to try to reconstruct what happened early on. Eventually, they just say infinity equals infinity, and we can't get past that point. So we need better equations. There are ideas about what happened in the very early universe that are very promising, so-called inflation, and we may be able to learn more about the early universe observationally from studying gravitational waves, in fact, which give us very pure signals, because the gravitational waves interact very weakly with ordinary matter. They give us a kind of unvarnished window into the extremely early universe, when things were moving around really fast and things were dense, and they make gravitational waves. So we probably will have more observational evidence, but we'll also need new ideas to get there. What's encouraging is that the picture of the early universe that emerges from observation and our current theoretical ideas is amazingly simple. So the fact that the answer, in a sense, is simple suggests that there may be a way to understand it that we can get to. You know, if things were just complex and messy, and we needed a lot more observational evidence to understand what was going on at all, to get a picture of what was going on, then it would be hopeless. But it doesn't appear. I mean, it appears that relatively only a few facts about the early universe are really necessary in order to characterize it, and maybe a profound theory would be able to account for those facts. What else can I say? So we don't know. It's a great question. What started it all? The form of of physics that we have today really doesn't work that way, in a sense that the most fundamental equations tell you, okay, if you have A at a certain time, then you'll have A prime at a later time, or A double prime at an earlier time. You can run the thing backwards and forwards and see how things evolve and change, but you need to start somewhere. You need to start, and the laws don't tell you how to start. What we found in cosmology is that the simplicity seems the most simple and profound state of the universe was in its early state. The Big Bang was very homogeneous, in a sense, very easy to characterize and understand, but we have to start somewhere, not at time zero. And if we and wherever we start, if we go back far enough to earlier times, we get our equations break down.
And your earlier remark about time is also something that I believe you mentioned within the book. It was like, it has to do with the time itself, right? Because before the Big Bang, you know, metaphorically, not metaphorically, but quite literally speaking, there was no time. And this is something that I cannot remember what exactly you wrote. Maybe I have it written somewhere here, but
this was a question that St. Augustine considered.
Yes.
One of his parishioners asked, what was God doing before he created the universe? Which is a very similar kind of question. And Augustine's first thought was to answer, was creating hell for people who ask questions like that. But he thought he wasn't satisfied with that, and took it very, very seriously. And Book 11 of St. Augustine's Confessions is devoted to this question about what is, and he thought very profoundly about what is time. And well, to simplify greatly his discussion, basically the conclusion he came to is that time is what clocks measure. Time is what clock. So, you know, if you really analyze what people mean when they talk about time, and what the experience of time is, it's something that everything in the universe evolves according to, and it's in particular clocks can stand in for something that responds to time in a predictable, regular way that's easy to interpret. But then it said, okay, but before the beginning of the universe, there were no clocks, or early in the universe, there were no clocks. So there was no time. And so the question doesn't make sense, what happened before. And it's quite possible, I think probably the ultimate answer that physics will come to will be something along those lines. It will be fancier in terms of concrete equations that are connected to other things we understand profoundly. But ultimately, we'll find that, I think, that the question of what happened before the Big Bang is, although it seems to be a meaningful question, turns out when you really analyze it, not to be. That nothing, there was nothing before the Big Bang, or the question itself, the whole concept of before breaks down.
Okay, I think I kind of understand it, but that's about the past, like even before the past itself, if you will. But okay, so that was one side that I previously mentioned of the Big Bang thing and the universe itself that really caught my attention when I was a kid, and like yet again right now after reading your book and after being exposed to materials such as shown on National Geographic. But the second part is about the future of the universe or the cosmos itself. And I remember, like, this might be totally wrong, and I might be just quoting it from my own memory, but I remember that previously I have read two seemingly contradictory things about the future of the universe. The first thing is, like, the universe is unlimited. I'm not sure if that's the right word, but it's unlimited. But secondly, that it keeps expanding. So how is it possible, if those two, sentences are correct, that the universe keeps on expanding despite its infinity?
Well, if you think about, to visualize it, let's just think about a plane, a surface, and it could be infinite, and yet you can imagine magnifying it, making it bigger. It gets bigger everywhere. And it was infinite, and then it's even more infinite, if you like, but it's the individual points move away from each other, but there's no contradiction between the points moving further away from each other and not having a boundary or a limit that you can just keep going, right? Yeah.
But I mean, more literally, into what? This might be, I might not be phrasing it right, but into what does the universe expand into? If that makes sense.
It does not make sense. Or not necessarily. I mean, it's conceivable that the universe that we experience in everyday life, and even in the most sophisticated laws of physics that we understand so far, which is 3 dimensions of space and 1 dimension of time, it's conceivable that they are embedded in a larger framework. Like, we can certainly see soap bubbles, for instance, that are 2-dimensional objects and in 3-dimensional space, and they can grow or shrink and even pop. And it takes more imagination to imagine 3-dimensional soap bubbles in a 4-dimensional space or a 5-dimensional space. But if you're trained in mathematics and know how to deal in the equations, you don't have to visualize. You can write the equations, and it makes perfect sense. And it's actually quite easy to imagine those situations in higher dimensions. And if the world is a soap bubble, it could just, it could also just, if you, there's no, it may be that it doesn't make sense to look outside the soap bubble. All of experience is confined to the soap bubble, and the other dimension, the dimensions in which it's embedded, could be just a mathematical convenience or fiction. You can talk, so you can talk about the intrinsic geometry of the bubble itself, and it, without reference to anything it's embedded in. So that's the kind of,
Yeah, I mean, it could
that in our models, in our currently successful models of the universe, mostly they are based on a self-contained geometry that doesn't involve embedding the three dimensions of space, or the 3+1 dimensions of space and time into larger structures. But that said, I mean, there are things called brain worlds. There are speculations about embedding things in actual bigger dimensional spaces, but they're very speculative, and there's no evidence for them at present.
But I mean, earlier you mentioned, of course, not the importance, but you mentioned imagination, and within your book, at the very end, you mentioned the principle, not the principle, but the concept of complementarity, complementarity, yeah,
complementarity.
Yeah, it's kind of, sometimes I have problems with pronouncing words that I used to pronounce really, really well beforehand. I don't know why. And I'm just going to briefly read the basic explanation about it that you've written. Is that complementarity is the concept that one single thing, when considered from different perspectives, can seem to have very different or even contradictory properties. I would like to ask you a twofold question. Maybe we can begin with the first one. How does the complementarity itself actually manifest in physics? For example, maybe to look at it through the perspective of actual Niels Bohr and his understanding that, that you can't really analyze the essence, the reality of something that you're analyzing it because you're interacting with it in the process.
Yes, well, the example from which Niels Bohr really extracted this principle of complementarity, well, I mean, there are hints of it in earlier philosophy and wisdom, but where he really emphasized it, advertised it, and advocated for it, was based on his experience in quantum mechanics, where it's really essential and unavoidable. It applies to everything. It applies to the world, the universe. But let's just in quantum theory. But let's just talk about an electron to keep things simple. So the primary description of an electron in quantum theory is in terms of what's called a wave function. And a wave function of an electron allows you to make predictions about what the electron is going to do if you make observations. But you don't really get to observe the wave function itself. The wave function is something that you process to answer questions. And depending on what kind of question you want to answer, you need to process the wave function mathematically in different ways. You have to apply different operations. So one kind of question you can ask specifically is about where the electron is going to be. And then to answer that question, you process the wave function in a certain way. And another question you can ask is how fast the electron is moving. And the wave function, which is a complete description, also allows you to address that kind of question. But to address that kind of question, you have to process it in a different way. And it turns out those two different ways are mutually incompatible. You can't do both at once. They interfere with each other. And that's a mathematical theorem in quantum mechanics. It's physical reflection is Heisenberg's uncertainty principle that says that you can't have both position and momentum or velocity determined at the same time. So that's complementarity in quantum mechanics, where, I mean, that's one example. There are many, many examples of a similar nature, broadly similar nature in quantum mechanics, that you can, depending on what questions you ask, you need to process the theoretical description in different ways that are generally incompatible. But each is valid. Each is a valid way of addressing different questions. Mm-hmm. It's just, you can't do both. I mean, I liken it to music, where you have harmony, which basically is the structure of the notes at one time and how they're sounding together. And then you have melody, which is a more global thing, which is extended in time and tells you about the relationships at different times. And you can either analyze the harmonies or you can analyze the melodies. But if you're listening, it's very hard to do both at once. You have to listen several times in order to really get that and do it separately. So in fact, those operations are very, very similar to the different operations on a wave function that you would do to get position and momentum. Position is like harmony and momentum is like melody. It turns out. That's not obvious, but it's true. So that's an example of what Bohr thought was a much, much more general philosophical situation or aspect of reality, that to answer different kinds of questions about the same object or the same situation or the same conceptual structure, you may need to use different concepts that are mutually incompatible and even seem contradictory superficially, but both are valid and both are useful ways of addressing different questions. So an example that I really like is free will and determinism, where a lot of ink has been spilled on that. And there are very strong arguments on both sides that there is free will and there is determinism. And people talk past each other. And I think the answer is there's both. And they are both concepts that address different kinds of questions.
I mean,
I even think I've started to understand that, by the way, in a more deeper way. Let me, you'll indulge me. This is something I've just been thinking about. We have an analogous situation which we do understand very, very well in computers. In computers, for various purposes, it's very nice to be able to have random numbers, right? If you want to sample different situations in an unbiased way, if you want to have computer games that are different each time you run them and unpredictably, it's very, very useful to be able to generate random numbers in a computer. But a computer really can't generate random numbers. It's a deterministic system. So there's something called pseudo-random numbers, which you can generate by doing certain processes that really scramble. You take a seed number and then you scramble it in different ways. And it looks very, very random after the scrambling, because the processing really distorts the original properties of the number in ways that are very difficult to work backwards from. But under the hood, it's deterministic. So from the point of, so it's both deterministic if you know the whole process, the underlying process, if you can look inside the hood, but random if you don't. If you only have a limited amount of time and a limited amount of ways to test, it really is random for all practical purposes. And I think that is a very good model for this whole issue of free will versus determinism, that the underlying sort of God's eye description of what's going on in the brain or in the world could be a deterministic description. But if you don't have access to the whole thing, like our conscious minds don't have access to everything that's going on in our brain, but only a limited thing. And for practical purposes, if you only have a limited amount of time to process information, it's not useful to have this deterministic description, which is in terms of equations that are very difficult to solve, and in fact, basically impossible for practical purposes. Then introducing concepts of free will are extremely useful to describe the limited perspectives. I mean, in fact, they're indispensable. That they are the useful ways of addressing those questions.
Yeah, two viable solutions, and either one excluding the other, basically, in this regard.
That's right. They're appropriate in different circumstances. They're appropriate to answer different kinds of questions, and each is really important and useful in its own way.
Yeah, and just as you said, it's upon the principle, not the principle, but the concept of complementarity that actually dictates the dictum, if you will. It depends on what kind of a question you want to ask, because that will dictate the way that you'll, in layman's terms, in my case, come to a solution, and how you will model the solution in the process. And I think that's one of the most beautiful things about physics and the world in general, is how one thing from a seemingly totally, different field can help you understand, like how physics in this example can help you, to make sense of the free will versus the determinism problem.
Well, to me, the most beautiful thing, I mean, maybe the most incomprehensible thing about the universe is that it's so comprehensible, but I think the most wonderful thing about the universe and understanding physical reality deeply from a human perspective is that it really expands your mind. It forces you to use your imagination. It reveals beauty that you didn't suspect in the world, and is full of surprises. So it's a huge mind expanding exercise. I call it being like being born again, to re-engage with physical reality. You have to unlearn things as well as learn things, and it's a real gift to be able to experience that kind of mind expansion again, not just as a baby where you're learning things, but when you use all the instruments and all the logical thinking that are available to adults, you can do a better job of understanding reality. And it's a great opportunity to expand your mind and experience the world in new ways.
Yeah, there are so many mysteries, and as in one of the quotations you put in your book, which we're, by the way, gonna put in the description below, so that everybody who is even remotely interested, and everybody should be interested in the world itself. I mean, and this ties in with the quote, with the citation or the quotation itself from Einstein, who said basically, if you're not indulging yourself into imagination itself, it's almost as if you're dead because your eyes are closed. And all of that you mentioned, Professor Wilczek, I believe is a beautiful message to end our conversation. But prior to us ending it, is there anything else that you'd like to share? And are there any new books in process, or are there any new things that we can look forward in regards to?
Well, my life is full. I've really been thinking hard and coming up with some new ideas. And most of them are pretty technical, and probably we don't want to go into it. But here, I mean, there's not time. But I am, well, it's a wonderful time to be alive, I think, but not only in the physical sciences, where we've learned these, we've gotten such a profound and surprising understanding of matter that's wonderful in itself, and also allows us to ask these ambitious and hope to answer these questions about the origin of the universe and strange things that are going on. And but also it's the time when I think we can really engage with the question that I intended to focus on when I started my scientific career before I got diverted into physics, which is the question of mind and how mind emerges from matter. Now we're building our silicon friends, which are very powerful, and learning how to teach them to think better. And I think we can. And so now I'm going back kind of to that kind of question also. Now that it's ripe for mathematical treatment, I think we have a real hope, a real chance to understand in a profound way how mind emerges from matter and re-engage with the kinds of seemingly naive but actually extremely profound questions that the ancient Greeks wrestled with, and expand our minds in new ways, both by understanding ourselves better, but also by creating new kinds of minds.
Thank you very much for that. I'm not sure how visible it is on the webcam, but once you mentioned how, your inquiry into how does mind arise from matter, basically my eyes teared up from the excitement of the question itself, because it's such a profound question. And thank you very much for that. You have my promise that after we're done with this conversation, I will Google that and see what's known about it. And thank you very much. Thank you very much for the inspiration. Thank you very much for your work, and thank you very much for your time. In the end of ends, I hope that there will be a second opportunity to talk, and maybe, who knows, talk about how does actually mind come from matter itself.
And new kinds of minds.
New kinds of minds. That's another, it's a meta mind, basically.
Yes. All right, thank you. It was exhilarating. Thank you. All right.
Thank you very much. Have a splendid day.
Bye now.